Okay.
Hello.
Hello, everyone. Welcome back. We are pretty lucky to have Adele Diederich from Jacobs University Bremen as the keynote speaker today. Adele is a professor of mathematical psychology. She has done a lot of work in the cognitive modeling field, especially mathematical modeling of cognitive processes like multi-alternative decisions and multi-sensory integration. Adile, I hope you are fine today, and many thanks again for accepting the invitation. Go ahead, please.
Okay, thank you for the invitation. Can you hear me?
Yes, of course.
All right, and so you can see also my screen?
No.
Sharing.
We have a black screen.
Okay. I think that is on your side. Can you just see? So I have sharing is paused. Bring your shared window to the front. And now I click on resume share and nothing happens.
خانم اصغری میتونید این درست کنین قسمت رو؟ فکر کنم شما هستید. We want to fix the problem, please.
Yeah. All right. All right.
Hello.
Okay, share. I start again. Can you see it now?
Yes, it's great now.
Okay, perfect. Okay, so then I just move on, and some people are in the waiting room. They want to get in. Okay, so someone should do this then. Okay, so I just move it then. Can you? Oh, gosh.
Dear professor, I will do. I will handle the queue.
Okay, thank you. Okay, so then let's just start me again. So thank you for the invitation, and I will give you an introduction to cognitive modeling. Then I will provide an example so that you can see step by step how this is done. So this is then a short overview. So I will give you then first the cognitive or the single steps of cognitive modeling. And then I provide an example so that we know what we are talking about. And then I give you the mathematical framework for it. And then we follow exactly the steps as described in the cognitive modeling procedure. So what is cognitive models or what is cognitive modeling about? So cognitive models aim at scientifically explain basic cognitive processing. And I heard that you are all familiar with this kind of approach already. And this here is, of course, perceiving, learning, thinking, decision-making, and problem solving are typical topics in cognition or in cognitive psychology. And these models, of course, want to try to explain underlying processes and also how these processes might interact, for example, perception and decision making. So they are derived from basic principles of cognition. So this is very closely related to psychology then, of course. And they use formal mathematical or computer language, and they describe human information processing at an abstract and mathematical level. And they serve to bridge between behavior and its neural underpinning. Oh. Okay, so I give you then first the steps. So the first step is that you take a conceptual framework from psychology or from related areas and reformulate its assumption into a more rigorous mathematical or computer language description. And use these basic cognition principle of the conceptual theory to construct the model. So we do not start from nowhere. So of course there is something around, but we want to make it more precise and develop it then. So, and if the conceptual theory is insufficient or too weak to completely specify the model, or is important, or if important details are missing, so then you are supposed to make additional assumptions. So when you are familiar with conceptual theories, you see there is a lot of words. So, and they are sometimes very unprecise, and we do not really know what they mean by that. And so, and then we need to make a little bit more, assumptions. So how the relations are, for example, larger, smaller, also what they actually have in mind. And then we need to have some extra assumptions, but also, as we will see later on some specific processes or some distributions. So that is often ad hoc assumption. But we do not want to make too many of these assumptions. So try to minimize the number of ad hoc assumptions. So the next step is then derive predictions from the model. And this is can be done in several ways. So for example, you simply insert, so most of all, or all models have parameters there, or almost all models. So, and then you can just plug in some parameter values, insert then in your equations, for example, according to a grid, and then you see what the predictions of the model is. And then you might want to look for qualitative and quantitative patterns. Sometimes when you, for example, do not plug in specific parameters, but you can say something about the relation of the parameters. One is larger than the other one. So you might even end up with qualitative predictions. And then you can just test this or specify it further in by inserting specific values. And then you can also have a quantitative pattern. So the next step is connect the model to data. So there is no good model that has zero connection to data. So you probably know I'm also the editor, chief editor of the Journal of Mathematical Psychology. And sometimes I get papers, they simply take a mathematical model and then they say, this reflects the brain, but there is zero connection to data. And of course, that's not a model we are interested in. So simply, having some equations and saying this is how the brain works is not what a cognitive model is. So we need to have some data. So that includes that you formulate testable hypotheses, and they are related then to experimental conditions. So for example, you want to do something with time pressure. So you present the stimulus material under no time pressure, so no limited time, or a lot of time pressure, so that is just very brief. The participants have time to respond to this. That would be, for example, a condition, and that's then also related to a hypothesis. Okay, so then the next step once you have, of course, done the experiment and everything, then you estimate the parameters from the data. And when a non-parametric model is used, so you can then compare the qualitative patterns to what is in the data then. The fifth step is compare the predictions of competing models with respect to their ability to explain the empirical results. As you all know, all models are wrong, but some are useful. That's quote. The quote is attributed to George Box, and at least in our profession, often people say this is my model and my model is correct, which is of course is nonsense. So they are all wrong, but some are a little bit better than others, and or can explain the data a little bit better. And so they should be, all the models should be falsifiable. That's just philosophy of science. And when a model is falsifiable, well, you cannot test it, and then it's useless. Okay, so you cannot, for example, explain the entire world by adding trillions of parameters, and it has no meaning, right? So that it must be testable, falsifiable. And then the next is then, of course, when we compare it, which model provides a better presentation of the cognitive system that we are trying to present. And they are models. They are models as data fitting tool, but I at least do not consider them as cognitive models. They are more or less like statistics. We come to this at the very end. And sometimes they are those who have just many parameters and do not make actually predictions, because they are based on some simulations. It's hard to make any predictions. Then they are often called measurement models, just to measure it, but for the situations. While the cognitive models should be explanatory, so they have some ideas why that is so. All right, and the last step in the modeling cycle, I would even call it, is reformulate the theoretical framework and construct new models in light of the feedback obtained from new experimental results. So that you can modify it, the model, just having slightly different assumptions, or expand it, so adding even something to this, or discard it because it is hopeless. So there is no rescue for it because it cannot explain the data at all. All right, so now I will exemplify these steps with an example, easy enough. I'm not so sure what your background actually is, but besides this perception, intersensory facilitation, and so I do a lot in decision making. And I take this example because it's easy to understand and shows nicely how a large proportion of psychologists do just use words and construct models which are, well, hard to test because they do not really make predictions, right? So what is then test? It's usually after the fact. Anyway, so this is then very famous. This is risky choice and framing effect. And in framing effect is a cognitive bias in which people react to a particular choice in different ways depending on how it is presented. And they are all kinds of different framing setups and also effects then, of course. So one is risky choice framing, attribute framing, goal framing, many things. And I start with the first, or I only will concentrate on the first one, the risky choice framing. So what is the experimental setup? So there are choices between two options, and one is typically a lottery, or they are lotteries, and one option is typically riskless, and the other option is a risky choice, like a gamble. And now we can put a frame on it, and in one situation, the outcomes are framed as gains. That's then called the positive frame. And in a second one, the outcomes are framed as losses, which is called then negative frame. So I show you in a second what that is. So for example here, so we have two choice options. In case you see my cursor, I'm now here where the choices are. But prior to it, so you get an information. So you are given 100 points in this experiment, And in the next step, you have then these two options here, still reminded that you had 100 points. And you have to choose between a sure option, so that you keep 60 of these 100, or you have a probability of this red area, resembling this red area, to lose everything, and with blue probability that is indicated in blue here on the left-hand side, that you can keep everything here, so that you can have the entire 100 points. And but in the worst case, so simply you lose everything. So that is called a positive frame. So in another one, that's loss frame. So you have exactly the same situation at the beginning. You are given 100 points. Again, you have then in the next step the option to choose between a sure option and a gamble again. And now you see the gamble is exactly the same. So we have 100 points with the blue indicated area resembling the probability to keep everything. Then the red one, 0, and the red area is then proportional to the probability. And here you lose, and here this is a sure loss, so you lose 40 points. However, well, that's exactly the same, right? When you keep here 60 means you do lose 40, and the same is true here. So you lose 40 and you keep 60. However, this wording, just this wording, has a tremendous effect, tremendously. So here we have these typical results. So in a gain frame, so the sure option is preferred over the gamble. So that's called often certainty effect. So when we have this game frame, the participants go for the sure option more often than for the gamble. And when we have the loss frame, then the gamble is preferred over the sure option. And this might result in preference reversals. So in one situation, more than half of the choices are in favor of A, let's just say. And when we have then a loss frame, then more of the choices are for B, let's just say, right? So that is a preference reversal once the 0.5 line is crossed. And a shift in preference is when it is simply different from one situation, but still in the same more or less field or area, let's just say above 0.5 and below 0.5. So these are very typical results. So, and the most popular account for it is prospect theory. I'm sure many of you are familiar with this. And so their explanation is that outcomes that are obtained with certainty are overweighted relative to uncertain outcomes. That's then the certainty effect. And in the positive domain, the certainty effect contributes to a risk-averse preference for a sure gain over a large gain that is merely probable. And in the negative domain, the same effect leads to a risk-seeking preference for a loss that is merely probable over a large loss that is certain. Okay, so this idea, the frames and the setup, and so that triggered a lot of research, and also in neuroscience. Here's simply one that was actually published in Science. So they have frames, bias, and rational decision making in humans, and they don't have a model, but they have fMRI and everything that is needed to have shiny data. And but what is interesting in this context here, that they actually proposed in the brain, so they are different areas, and in the brain that they are figured out, or by doing experiments similar the ones I just proposed there, that there are two neural systems, and one is more analytic and the other one is more emotional. Okay, so they tie it to some structures in the brain, but that's not so important in this talk here. So that is analytic and emotional, two systems. Okay, so in a different research group, so they also have the idea, they do decision making, and they also come up with the idea that some regions of the brain are more heavily involved in one thing over the other. And they conclusion is also that they propose that is a dual system framework. Okay, so they have these, the done for intertemporal choice, risky decision making, and social preference, and they call these dual approaches then effective system and deliberate system. Okay, so but when you look into the history of dual processes, so they are applied to many, many different areas, including reasoning and judgment. And when you just see here, so what kind, and here's the generic term system 1 and system 2 used. So you see that here they are described. System 1 has all kinds of different attributes here, depending who did it and in what area it is. But here, for example, automatic controlled, here's the system 2 here, and is one that's interesting, or heuristic and analytic, similar to what we just have seen. And what else do we have? Reflective, I don't know, that's not so important. Impulsive, reflective, and so on and so forth. So they are lots of different descriptions how they are. And one is, what is important for here is one is fast. System 1 is typically called the fast system, or this intuitive system is fast and is biased, emotional. And the second system is deliberate and is slow, rational, and gives normative responses. And this approach, in particular in decision-making, became very popular with the book by Kahneman, Thinking Fast and Slow. So the problem for most of these approaches, and those in the list, most of them, they are verbal. They do not allow for quantitative predictions. And this is totally unclear what the processing is. And they use reverse inference. So as I said, one important feature of these systems is that one is fast and one is slow. And reverse inference is when you give a quick response, then it's attributed to system 1, and when it is a slow one, it's attributed to system 2, which of course makes no sense whatsoever, as we will see, or as you can imagine. So they are a few formal models, but not really, I would say. So they are more or less algebraic models. They have no time mechanism, so no dynamic, and it is also not clear what the processing actually is. So now we start here how we do this. So we have a conceptual framework. This is very popular. We have that in many, many different areas. And so the assumptions, they are, here we have seen that in the list. I'm not repeating them again. So keep in mind, one is called, or one property is more the bias, the emotional one, and the fast one. And system 2 is more the rational one, and the deliberate and the slow one. So that's important. And the question sometimes is, do these systems work in parallel or in series, or are they working serially? And the majority of researchers assume that they are serial processing. However, they simply say so, because this is just words. And okay, so we want to construct a model for this. Okay, so we have then from our side, because that's not very precise, I come to this back again. So we say that the consequences of choosing each option are compared continuously over time, and these preferences are constructed. That's just what we assume. And the preference accumulation is a process with preference updates. I come to that in a second. And there is random fluctuation. So these are kinds of assumptions we make. They do not have anything to do with the system 1 and system 2 per se. But for our approach, it's important to assume this. Okay, so the framework I'm using for this then is a so-called multi-stage decision model or multi-attribute attention switching model. I use different names for the same thing, and that serves here as a framework. And this model belongs to the class of sequential sampling model. It predicts choice probability and choice or choice. It predicts choice. Probabilities, I should have said, and choice response times, and it is linked to a fact in biology that evidence accumulates, and there are typically thresholds. Here I provide some papers with the derivations of just the derivations, not the applications. So these are simply derivations then. All right, so let's just go to our first assumption back. That is, the preference strength is updated from one moment to the next. So that is, once I see these options, so the sure option and the gamble, so my preference for one or the other is updated from one moment to the next by reflecting the momentary comparison of consequences produced by imagining the choice of either the gamble or the sure option. Right, so then the gamble, okay, I can get more, but I can also lose a lot. And the sure option, I know what I get, right? So I compare, the decision maker is comparing it. And of course, comparing it and eventually deciding takes time. And there is then that the preference strength or changes over time. So there's an update. So that's then here indicated. So here we have our preference strength, and then we have a valence. So that's called, or in psychology, then you probably know. So we have an input valence, and that is simply how I like the gamble and the sure option. So that is, I compare again these two options here. Time at a given time, and this gives me a valence. And so this is the momentary valence for the gamble, so I like to have that, and that is here the momentary valence for the sure option. And so I compare them, and then the result of this comparison is added to the preference strength. So I heard you are all familiar with the stochastic processes, so I do not have to explain here a lot. However, just to be on the same page, I will simply tell you a little bit about what we use for this process here. So very general, has nothing to do with a more complicated process, but this is an ingredient of this. Okay, so we have a starting point. So that's the initial state of a preference strength. And then in this cartoon here, it is assumed that is unbiased because the distance from here, can you see my mouse by any chance, my cursor?
Yes, of course.
All right, perfect. So you see here, the distance from here to here is exactly the same from here to here. And so in this case, we say the person or the process is unbiased. So the person in our scenario has neither a preference for gambling, not for a sure option. So when we then move that up, because here this is already our boundary here. So everything that is here is then a choice for a gamble and here for a sure option. So when the process moves up here a bit, not shown, then the person has an a priori bias towards choosing a gamble. The same is true when the starting point is more here. So then the person is a priori, before even seeing anything, biased towards having a sure option, choosing the sure option. So in this one here, we have the starting point or the initial state is fixed. However, as you know, we can also have a distribution across this here, right? So then we have a distribution, and that's then all called the a priori bias. So prior to anything, the person has this, and that is then reflected where the process starts. Okay, so the increments I said already, so or that we do an update from from a moment to moment, and then the increments of the preference sampled at any moment in time is such that when they are larger than 0, they favor the gamble, and when they are smaller than 0, they favor the sure option. So you see this wiggling around, and each trajectory here is basically one trial. And I should mention that, and I will mention that a couple of times, this is not observable at all, right? So here is just, I just simulated them. So 3 trajectories. And in this one here, it is more towards the gamble, or it's actually a gamble choice decision. And you see these going up and down is simply that this results from the preference update. So that is then these models assume that there is a continuous update of preference trends. Okay, so the drift rate is very important, one of the most important parts in all these models. And this is simply here, this one, the drift, is the valence difference determines the drift rate. And the larger the valence difference, the larger is then the drift rate mu. So that means when I have then large inclination to choose the gamble very large, then it would be steeper here, right? And okay, so I don't have to tell you this, what that is, because you are all familiar with this. Okay, so in this cartoon, we have 3 drift rates. So we have, again, we have our gamble and our sure option. And so here, as I said, so this here would symbolize that there is a strong preference for choosing gambles. And this one is less here. And this here is actually indifference. So you see here the dashed line, that means here the person would be, well, not care the gamble or the sure option. So indifference between choosing the gamble and the sure option. And the negative drift in our how I labeled the, well, in our notation would be then for the sure option, right? So that I'm omitted this. Okay, so then the criterion. So we assume that the process stops and response is initiated when a criterion is reached, and the criterion is set by the decision maker. So internally, we cannot observe it, but we can estimate. This is part of the model. So what this criterion can be manipulated by instructions. So for example, be very fast or be very accurate, and all kinds of strategies and the decision maker might have. And so these here the boundaries are under the influence of the decision maker. Sorry. Okay, so and then we assume that when you put a deadline on a trial, so the trial or the participant has to respond within a preset deadline, otherwise get penalties or so. So then these kind of models assume that then the boundaries are lower. So you see here is the time pressure situation maybe, and then we see that has an effect. Okay, so I chose exactly the same. Okay, so in this case, we see that then the gamble was chosen here without the time limit. We don't know yet, right? So it could be just go down easily as well. All right, now we are ready for the real model to model the dual processes. So these models I'm working on, the multi-stage decision models, the one basic assumption is that for each attribute, in a very, very general way of thinking, so for each attribute of the choice alternatives, a different accumulation process takes place. And now we are ready for applying this framework also to the dual process models. So that means for each system, a different accumulation process takes place. And so each is missing here. And they are, of course, according to what the researchers in this area think, they can be serial processed or parallel. And first, I consider the case where attention switches from system 1 to system 2, and they are processed serially. So system 1 comes first and then followed by system 2. Because according to what the researchers claim, system 1 is the fast one, so that should come first then, and then later on system 2 kicks in. All right. So the next step in our cognitive modeling is derive predictions from the model. So we said that this can be done qualitatively and quantitatively, and I want to first go for the qualitative patterns. So in the following, I simply have 6 trials, and the expected value of the sure and the expected value of the gamble is the same here in this case. So the person is then risk neutral. And then of course we can also have different ones, and then we do not have, then we have risk attitudes, but is just minor, it's just to make it complete. Okay, so let's just put this one here. So we have here now the ideas of the dual process implemented in this frame here in our stochastic process. And here we let's start with the gain frame. So here we have system 1 comes first, then followed by system 2. Here is the boundary for making a gamble decision, and here's the boundary for choosing the sure option. And in this case here is, so simply the process starts, and then there is in the gain frame, we said that the people predominantly choose a sure option. So the preference goes in that direction. And then after the second, and that is process operating on system 1, but then system 2 kicks in. Now, because the expected value of the gamble and the sure option is exactly the same, the person should be indifferent. And indifferent, we have seen, means that the drift rate is 0. Okay, so that is this case here. And then and here's just switching, and I did it here as if it's to a particular time because it is easier to draw in a cartoon. However, it could also be a distribution. Okay, in the second situation where we have a loss frame, we know from observation and from the data from past experiments that in those cases, the participants, the decision maker, most of the time goes for the gamble. And so in system 1, then the preference goes towards this boundary. And then after some time, the second system kicks in, and then it is clear, okay, that's again, the expected value for the gamble and the sure option is the same. So then the drift is then 0. Okay, so now I skipped this here briefly. I simply mention this also. We have a game frame and a loss frame, and we can have different attitudes from a person, risk averse and risk seeking. And then of course, that is not a 0 drift. It is simply 1 according to the person's risk attitude. So that can also be implemented. Okay, so next step is predictions. So the first prediction is the size of the framing effect is a function of the time the decision maker operates in system 1. And the second prediction is the size of the framing effect is a function of the time limit the decision maker has for making a choice. Okay, so let us have a look at the first prediction. So the size of the framing effect is a function of the time the decision maker operates in system 1. You see here, so the this emotional fast I wouldn't say irrational, but emotional and not really precise system, is only the decision maker only operates for a very brief time in this one before switching to system 2. And then you can see, well, everything, the inclination to choose the sure option, well, is still there, but overall it is leveling or canceling out, because again, we do have a rational decision maker should be indifferent between the gamble and the sure option, because the expected value is the same. And then we could expect that after a long run, so that basically half of the responses go to the gamble and half to the sure option. So that is only very briefly operating in system 1 before the more normative, more rational system 2 kicks in. A different story is when we have this here, when the person or decision maker operates in the system 1 for a very long time. And then we see that most of these choices here, or the trajectories, are absorbed, meaning that the decision maker goes for the sure option more often, because then system 2 kicks in rather late. Okay, so that would be a qualitative prediction. So simply by seeing what effect by stretching the system 1, so the decision maker operates longer in system 1, has. So the second was with respect to deadlines. So the size of the framing effect is a function of the time limit the decision maker has for making a choice. Again, so we have here, let's just say no time limit, and then the person is set under time pressure, the boundaries get in. So in this case, so I choose exactly the same trajectories here. And then you can see, well, when you have shorter times, this would here absorbed already. However, that might have been, then that this goes to the other side or so. You see that then a lot of these are absorbed already there when we have shorter time limits with a given time in system 1 as compared to longer ones. Okay, so these are the predictions. Oops. So then when we have quantitative predictions, of course, then we have to say something about the parameters and the values. Okay, so in this case here, I choose the following. So system 1 is the preference in system 1 are constructed according to prospect theory. So we said that is the most prominent theory in for explaining these framing effect, and that's attributed to then system 1. So system 1, or prospect theory, operates or builds the preference when the decision maker is operating in system 1. And in system 2, we have expected utility theory. As you know, this is a normative model. A rational decision maker should then behave according to expected utility theory. And this is then in system 2, because that's exactly how the system is described. Okay, I don't know exactly how much you know already about the different theories, so I just put this here then together. So this is system 1, and we said prospect theory is forming the preferences, and we have here so evaluation and an evaluation of a probability. And so this is then a probability weighting function. So that is according to this here, that's the most popular, the most widely spread assumption. And then also a value function. So we have values and probabilities, right? Like the 100 and the 60, and then the probabilities, the shaded in blue and red, and they of course can be quantified and they are translated accordingly here. So here we can have all the different probabilities in our experimental setup, for example, And then we have some parameters here. So these are the parameters. And for the value, so this 100 or 50, whatever, how many points you can have, or 60. So we have then, this is here the axis. So then we have also parameters. So how then, not the utility, they don't say utility, but they say value, how the value for a certain points or money is built. Okay, so that is from the literature, right? So this is not invented by us, let's just say, but this is how preferences are built according to some theories. Okay, so this is then system one. We have here our the weighting function. So that is of course a probability, and typically you know that you do not fiddle around with any probabilities, but in this theory it is. So that means larger probabilities, smaller probabilities are overweighted and larger probabilities are underweighted. Okay, so then we have here the value function is the next ingredients, and we have, depending on the loss and the gain frame, different forms. And so they are formed like this one here. So we have the gamble is always the same. And then we have the sure option in the same and in the loss division, because the gamble, as you have seen, is always the same, regardless of the frame. It did not change, but the sure option and the loss option does. So one is said you can keep it, and in the other condition it was you lose it, but it is exactly the same. Okay, so then we have the weighted probability times the value of the gamble and so on for these three. And then for the second system, we simply assume expected probability here. So the probability is the probability here. And to make things easier, so we assume no utility as such. We assume that this is expected value. So the value is exactly the value. So that means the probability times the value that is offered. And that is then our expected utility or expected value. Okay, we are almost ready here. So we have now, according to our agreement, so that's the probabilities, the preferences are constructed. And then what is basically, yeah, the construction as such that is mapped onto or the summary of it, I should say, is mapped onto the drift rate. Okay, so we have now two frames, the gain frame and the loss frame in system one. So, and this is here the equation for the drift when we have a gain frame in system one, a loss frame in system one, and system two is the same for both situation, and this is mapped onto mu2. Okay, so that is 1 for system 1, and this is here for system 2. Okay, so now to make then predictions, we have to have some concrete values. So we have here different reference values here. So 25 points, 50 points, 75 and 100. So that's always given. And the probability of keeping them is here 0.2, 4, 6, and 8. So this is changing accordingly, and that is changing according to these numbers here. Okay, so lots of different combinations. And I took the parameters just to make a quantitative prediction before doing any experiment that is found in the literature. So that is system 1 has, according to prospect theory, these parameters. So we have seen alpha, beta, gamma, and lambda. And we have for the system 2 no parameters because we said it's expected value. And then we have the boundary and we have attention time. That means when it is switching. And I did not say what kind of distributions they are. So when it's not fixed, then it's of course an expected value of it. So that is also part of the model. So when we do that, then we can, here's a very busy slide. And we have here the loss and here the gain frame. And one was the size of the framing effect is the function of the time decision maker operates in system one. And this is simply saying here the T1 when it switches from the first to the second one, right? First system in the second system. So here, when we have that, immediately going to the rational system. So basically ignoring system one. And then we can see it is accordingly to the normative model always on this line. And then we expand that. So that means here 100 time units, 500 time units, or only staying in system one. And then we have here our predictions accordingly. We don't have to go to all the details here, but you see it's changing in a systematic pattern. So that means that is saying that in a loss frame, the person takes the only operating by the system one, takes only the gambles, and in the gain frame is taking only the sure options, right? So that's what it is. So it is getting extreme when the person only operates in the system one, which is as intuitive and emotional, called intuitive emotional. So these are the probabilities. So probability of taking the gamble. Okay, so here I make a shorter one. So I skipped some of the probabilities here, and attention times. So this is a second, this is with respect to reaction times, right? So that is that we have the pattern as before, only a little bit shorter. So I took this one and this one here and make it like here. And these the according probability, the reaction times. So you know that we can also, what we observe is, I forgot to mention this, of course, which choice was made and how long it took. That's all we have, right? So that is the time and the choice. And these are our observations. And the model, I said, makes predictions with respect to choice probabilities and choice response times there. And that is how we compare it then, right? So we can, what the model predicts with respect to this, so first passage time is then related to reaction time, and first passage probability is to choice frequencies. Okay, so, and you see that you have a very rich pattern here. I don't have time. Do I have time to go through this here? And well, so you can just, you see that they are very different with respect to sure and gamble. And in this part here, so when we compare the blue ones to this one here, they are very different. So you can just yeah, you see that they are giving a rich pattern of choice reaction times. Okay, I say a little bit more to the more general later on, the patterns. Okay, so let's just do then the second prediction. So the time of the framing effect is a function of the time limit the decision maker has for making a choice. Okay, so we said the time limit is reflected in the boundary, right? So in the choice boundaries here. And now I have 10, 15, and 20 as a boundary. So that means 10 is the shortest and 20 is the longest. And then we can also see that this makes indeed a difference, not so dramatic as in the previous prediction. However, the size of the framing effect is 1. And you see when it is short, here 10, so then we have here a stronger framing effect as compared to when the time is long. Okay, so blue is always on top of red, and black is on top of red as well. So it is just the order as predicted. So also, or as assumed then, and it is also reflected in the quantitative predictions. Okay. here even more busy, but you see that is all possible, so that we have quantitative predictions, and we can test this. And it is dramatically different here, right? So it's very, very different. Unfortunately, I don't have time to go in all the details because I wanted to show you all the steps here. Okay, so the next is connect model and data, and this is then formulate testable hypothesis. That's what we have already done. So we put, for example, the decision makers under time pressure, and then estimate the parameters from the data, and then compare the predictions of competing models. So that is now done all together. Or first I give you another example. So for example, you competing models would be, we have system 1 in system 2, but this carries over in system, I should say it again. So we have preferences in system 1 follow prospect theory, and in system 2 it carries over. So that means the preference in system 2 are a weighted average of prospect theory from the first system and expected utility. And so in this case, the drift would be different, obviously, but the qualitative predictions remain as before. Not the quantitative, but the qualitatives are exactly the same. So then we have another competitor. So they have also system 1 and system 2. So system 2 as our assumption, so it is expected utility, but the first system is quite different from prospect theory. I have no time to go into any of these, but so it has an emotional function, and we saw that, we saw that emotions is part of system 1, and so that captures then the intensity of the affect, motivation, and then another function that reflects the willpower and the cognitive demand. I skipped all the predictions, and it is not really nicely in terms of mathematical strength or rigorosity formulated well. So it is not, so I'd made a grid then on these parameters to see how it worked, but I skipped this because of time constraints. Okay, so now it's all put together here. We take the data already, some data here, and now we can see that we can compare different kinds of models. So for example, prospect theory only, prospect theory and expected utility, and then this specific one, so by Lowenstein and colleagues. So we have then, as we have seen before, these different parameters, and they change names according to what they have here, right? So they have different names for this. And okay, so that has, of course, a lot of parameters, as you can see. So then we test models. That is typically, as you probably have already learned, so that when already models are out, you should test them. This is, I have to say, the framework was not out. That is unique. That was the very first time. However, how you model the system 1 and 2, that of course gives you a lot of freedom. And here are some different models. So prospect theory, then with a scaling parameter, dual with prospect in the first and expected in the second stage or system, and then dual process with prospect in the first and the weighted in the second, and so on. And this is system 1 with a scaling factor, and then in 2 stages, because they propose that's all collapsed on one parameter. Well, not they don't have a stochastic process anyway, but they do not differentiate timely between 1 and system 2 and 1. Okay, so now I show you just only the prospect theory, the dual as I just proposed, and then 2 other ones, and you can see that, oops. So then you have, here are the data, and that is typically what you can then see. So these are the model accounts. So the models are, the parameters are estimated from the data, and how this is done. Of course, I have no time to go into that, but I believe another talk will explain this to do how this is done. And all over, you see that the red line here is doing really well. And that gave the best fit. You see the data are very noisy. So that is, for example, not to explain, either they should be increasing monotonically, increasing here like this, or decreasing, but not going up and down as a function of amounts. That does not make sense, but this is the data. And then of course, all the models had hard time to explain this. Okay, and these are simply the different conditions here, so I'm not going into any details of this. So this is an article published, and you are welcome to see the data. So the last step is, basically the last is reformulate the theoretical framework and construct new models in light of the feedback obtained from new experimental results. So modify, expand, and discard. Okay, so let's us do parallel processing, right? So that could be was also some idea that is as parallel processing in dual processors. Okay, so typically what people then do is they collapse the information of all the attributes, or then in this context, then two systems, and have a sum and map this then onto one drift rate. And I should say these time processes, or the processes I just showed, they are not time homogeneous, right? So it's a Wiener process. I forgot to mention, it's a Wiener process basically, or an Ornstein-Uhlenbeck process. But in this case, when you do that back to back, and the starting point of the second stage is the ending of the first, they are not time homogeneous anymore. However, when you do this, they are simply very simple models then, right? So like a Wiener process. Or another one is they do a weighted average or a mixture of processes. So for example, in one trial, they only work on system 1, and in the next, they only operate on system 2. That's well debatable and is not really two dual processes. Then there is an independent race between alternatives or attributes, systems in this case. So there's a race between system 1 and system 2. However, when it is an independent race, and by default, the system 1 is always the faster, well, then it always wins the race. So then that would predict that all the responses are only made based on system 1. Okay, dependent race models are not really found. So, but we can, with this process, construct a parallel processing with dependencies. And this can be done like this. Here you can have, let's just say here, two different lines. So you have here, one goes, for example, to the gamble, and one goes for the sure option. And there is a switching, back and forth switching all the time. So basically that is now exaggerated here. So the time here, so you go from 1 to, you operate, or the person operates in system 1, system 2, 1, 2, and then you can just abbreviate this, make it very fast, and switching back and forth between the two different systems there. It's also dependent then, of course. So when I do that here, when I did this, I have different as the parameters as before. So they are from perspex theory. For system 2, we don't have any. The boundaries for short and long, and the residual times, that's typically not modeled. It's added as a constant, or depends on the model. You will learn more in later sessions. I saw that, how that can be done. Okay, so now you can have different structures. So serial, switch from 1 to 2, and then you have parallel, so you switch back and forth. And then you have to specify, of course, how this is done here. In this case, I did a geometric distribution, and then that is very convenient. But doesn't matter. So now we can have different models to test. Serial, as before, starts with system 1, of course. Then we have parallel, can start with any system first. Then we have parallel, starts with system 1 and goes back and forth then between system 1, or we have parallel and then starts with system 2 and then parallel back and forth. That's not really according to prospect when dual processes, because they say the system 1 is always the first. Anyway, so that gives also a very poor fit here. So again, these are the same data as before, now with 3 different models, and now the story is a bit different. So you see that the serial is not always the best, but still very noisy data, and that needs to be explored in more detail. It's just to show you that you can also modify it and then test the data again with a new model. So that's as before, reaction times under time pressure and not. Okay, almost done and almost, on time. So let me just conclude here. I hope, I know it was quick and many details were missing, but nevertheless, I hope you could understand what the steps of computational models are. And I try to give you an example for each step and how you develop this, right? So how you develop the idea and go from a conceptual framework and then ending up by modifying your created model. So what are the advantages of computational or mathematical models? So they force the researchers to give precise definitions and clear statements, as I said. So the dual process is mainly words and they change. And that leads to minimizing the risk of making contradictory statements in the theory. And they guarantee logically valid predictions and allow the derivation of precise quantitative predictions from the underlying assumptions. And they enable empirical falsification of the assumption. That's absolutely important, as you know. And then deriving predictions is particularly important and useful when they are not obvious. And this is useful for deciding between competing theories of a given phenomenon. So then it brings together the theory and data. We have seen that. It facilitates the analysis and interpretation of complex data and helps in generating new hypotheses. And so that's also important. So typically you interpret also the parameters with some concepts, psychological concepts you had in mind before. It's not always the case, but often you can do that. So then rather simple computational models often describe the data better and more informative than a statistical test of verbally phrased hypotheses. And then in contrast to statistical models, they are capable of generalizing their prediction to new situations, different experimental conditions, and new dependent measures rather than fitting and summarizing a single set of data. And they provide a unifying language and methodology that can be used across disciplines. And that's what you experience, right? So I heard that you are from all different backgrounds, and that makes it easier to communicate. And as some of you know, and the host for sure, so I'm working with someone from mathematics. He's original from Iran as well. And then of course, that is our common language and it works perfectly, right? So that's also good. Another thing I should say, data fitting. These computational models, often, or some of them, they are called then, or call themselves computational cognitive models, but they are often only data fitting tools, so they cannot make any predictions. And this is what I said in the beginning. So then they are more called measurement models, and there was a hype of it. I don't know whether this is still for much longer. However, I think real cognitive modeling is where you also have predictions and have some explanatory aspect only, and not adding more and more parameters so that you can have a nice fit. And that's it. And I thank you for your attention.
Okay, Adila, thank you so much for your great presentation. It was really very interesting. Everybody, any questions? Everyone can speak or write in the chat.
All right.
Hi.
Hello.
Hello. Do you have my voice?
Yeah, I can hear you, but I cannot see you because I'm still sharing this. Yeah, but I can hear you fine. Yes, please.
Thank you for your lovely lecture. I
Thank
really
you.
appreciate you.
Thank you.
Actually, I have two questions. First, regarding more philosophical, because I'm new to this field and I'm actually a mathematician. So, most of mathematical things based on axiomatic systems, which we believe that those axioms are established to be true, and many theories derived from those axioms. But I don't know exactly what are the actually psychological axioms, and how could we show that the models we fit and models we create, that we know they are computationally following the mathematical logic, which those are stemmed from axiomatic systems, are exactly those axioms that in general is in our brain. And it is a really fake to me, because I can't actually see any axioms in this field.
All
could
right.
you could you
Very good.
please
Yeah,
could you please give us a really little
sure.
detail on it?
Sure. Okay, so are you familiar with expected utility theory?
Yes, I know a little.
All right, so that's an axiomatic system, right? So that's called a normative model, and that is how people should behave, right? So you have axioms, and in particular, that is how they imagine how a rational decision maker should make a decision. In psychology, and that is this field here as well, we do not assume this. So that people actually follow any axioms and do exactly what they are supposed to do according to this axiomatic system. They are more descriptive, right? So, and that is exactly the same here. So here, for example, we take a stochastic process. In this particular one, I took a Wiener process. And of course, nothing is observable at all. It was not even created in for mimicking some ideas that is concerned in the brain, and or it's convenient because we have its time and some the stochasticity in it. And but we don't have an axiom as such. That is not, we cannot say, okay, the brain works like this and this according to an axiomatic system, and that's what it is. That cannot be provided by, not by computational models, no way. And if someone claims this, this is simply not true.
Thank you so much. And another question is regarding to unconscious experiences and unconscious thoughts. I'm not pretty sure that is there any kind of model that underlying unconscious experiences. Like we know that many psychological facts relying on like Freudian theories, that they are relying on unconscious. Like yes,
Freudian psychology or theories are not considered as scientific theories. And for example, I doubt, maybe in France, but in Germany for sure, nobody teaches that in university. So that's more like an historical anecdote, but not really providing some evidence how it really works. So with Freud and everything. That's no. But of course, there is research on unconsciousness, in particular in the context of attention. There's a lot, however, not with all the unspecified theory that was then built some 100 years ago or so. No, I'm afraid, and I cannot really say, but I know that this is not considered as a scientific theory, and therefore it's not taught in universities as such.
thank you so much. I really appreciate it.
You're welcome.
Okay, any other questions, everyone?
Can I ask a question?
Yes.
Yeah, go ahead.
Thank you very much for your very fruitful presentation, Professor. I have a question about the framing.
Yeah.
When you add the framing time to your model, you actually consider it at the trial level, and the dynamic of the the dynamic of the time framing and the switching time between the first system to the second system is not captured in the model. But I think that we have some, for example, we have sequential sample reinforcement learning models and something like these frameworks that captures the dynamic of the parameters through the through the experiment. Can we do such this to the timing the framing time, capturing the dynamic of the you know switching time when the participant is experienced with the task.
Yeah, I'm afraid I did not completely understand. The switching time is a parameter in the model, right? So you can estimate this. So you can assume what that, or you can have an idea when it is switching and when not. I had no time to go in all the details, but I provided the references to it. So the switching, how long a decision maker is staying in system 1 before switching to system 2 is a parameter estimated from the data.
Yeah, I know it's a parameter.
Yes.
But this parameter is for the task, for whole experiment.
Well, you can do it differently, but then you increase the number of parameters. And as you know, you should be you should have as little as possible. Of course, you can say, okay, I switch in a gain frame differently than in a loss frame. Absolutely possible. It's not a problem, right? So then you add another parameter to the whole because you estimate the data, of course, from all conditions time-wise, so under time pressure and not under time pressure. So they are all the same. And then, of course, you can also allow to expand it in terms of number of parameters that you say, okay, we have different boundaries given a gain frame and given boundaries given a loss frame, and also the switching is also possible that it is connected to the framing. You need to know, I mean, I'm sure you are familiar with this. By increasing the number of parameters, you have to have more and more and more data condition to actually test this. So you should not have more parameters as data points, and often in psychology is difficult anyway, so that you have to have lots of conditions so that you do not outnumber the that you have enough data points to estimate the parameters. Yeah, of course it is possible, and I'm not sure I did it. So maybe I even did this. However, to be as parsimony as possible, so you fix everything that can be fixed, or put it the same. Is this answering your question? Or?
More or less, but thank you for your answer. And the other question is more general. At the beginning of your presentation, you told a good paper should connect the brain to the model, and the model should present the brain, and this presentation should be done through the data. But there are very papers that are published without data, just a theoretical just a theoretical discussion on a based on previous theories, and I don't know.
Yeah. Okay. So I'm sure I know that there are fields where this is done. However, at least in psychology, you should have contact to data, because otherwise, how do you know that you are not totally off? And these models here are mainly on behavioral data, not on some functional imaging or so, right? So I'm very skeptical that from just observing the brain that you can predict any behavior at all. And psychology, or it's mainly on behavioral data, and I'm not, although then some areas of the brain are so related to this, is always the question whether this gives more evidence to whatever is happening. Yes, but I mean, it's just when you have a model and you say that this is how it works, in theory at least, you should be able to say how to prove it. Isn't this the case? So why would you otherwise make a model when it has no, so when it has no connection to reality or to the world? Or I misunderstood.
That's okay. I got it. Thank you so much for your answer and for your presentation.
You're welcome.
Great. Any other questions?
Actually, I have more question. I have a more question. You know, as you said that you are a chief editor of mathematical psychology,
Yeah.
I have lately rejected one of my papers, and it was a computational model of human memory with a cognitive approach, and I used some cognitive functions and philosophical approach to simulate how machine can learn like the human do. I mean, I just simulated, and then the editor rejected me, and the declaration was that you do not done some data research and data analysis on the real data, but it was just about machines and not more. And it was a question that how could I actually claim, and how could I um, suggest a new method that we could say this model philosophically should work like human, and we want to apply it to machine.
Yeah, okay. So typically, you know that science is accumulative, right? So when you want to do something on memory, then always a good idea is to see, or on learning, so what is already there. So what you don't have to collect data yourself. So let's just say there is a pattern. You see that there is a pattern that has been discussed a lot in the community and so on. And now you come up with your new model and say, okay, so I can explain this pattern because la la la, then you explain your model, and that's enough. You don't have to collect it, but then you make already connection to data to say, okay, so this is explained. So this effect or this empirical patterns can be explained by exactly that. And I'm sure I did not I mean, the learning and memory community is very particular, as you know, so they are from different areas, but they definitely want anything that is not reinventing the wheel, right? So that is, but once you said, okay, so you believe that this can be explain that result, let's just say recency, or was it on memory, right? You said? Or on
Yes, it's about memory and learning too.
Okay, so that you, I mean, how do we tap memory, right? So you ask people and then you see how many words they can recall or whatever, and all kinds of these things. But if you only have a model and said memory works like that without showing the connection to reality, yeah, is difficult. I can see that, or some, at least, yeah. What is it then on, right? So what is it
Actually,
on?
actually, it was about, you know, I did kind of clustering and categorization in semantic units. I use graph theory to
Mhm.
represent the semantic unit between each node is a if you see as a Gestalt view, is a kind of proposition, not
Mhm.
a word, and the edge between those nodes are the semantic correlations.
Yeah.
And it appear and I made some, you know, a weighted graph, and I made a terminology which was a mass-based graph, which each node has a unique mass, and each you know, correlation edge has its unique unique weights too, and then they are affecting each other, and with a more philosophical view, which says that like Wittgenstein's word, that we learn everything by at a time, without in each interval. And I made a dynamic graph, which whenever you learn something new, the whole dynamic graph changes. And it based on three major categories, which was evolutionary. For example, the words and prepositions attributing to, for example, sex or mother or guardians, and these are evolutionary. And so do I. If we see the reality of our life, we say that we do not forget the propositions regarding to these evolutionary and survival things. So I made a kind of induction by myself, and then I just made a dynamic graph, and then I applied it to a mathematical framework, and I did it to a machine learning way and neural network. But the editor was rejected me because he you know stated, or he or she stated, that I did not apply these methods to real data, which was derived from, for example, EEG or another
Hmm.
you
Hmm.
know, devices.
Hmm. Yeah, I mean, I cannot really say so. For me, it's really so when a nice method is proposed, so I don't, and they say they are for these and these kind of data. I have no problems with accepting a paper that has no data in it. Of course, there are tons of data papers without any data, but in principle, right? So in principle, you need to say how it is testable, how you can make the connection to something that can be observed, whether this is behaviorally or in a scan or by tapping on some neurons. That does not really matter. But in principle, you should make that happening, right? So you should make this connection then. So if it's just so, I mean, the model you described is sounded pretty much like spreading up activation. So now you can say spreading is a very old model. Spreading activation, it's just words, right? Not really a lot. So now you take this and say, okay, this spreading activation in memory and recall, that can be formalized exactly like what you just said, so in graph theory or your approach. So that is exactly what it is. So, and then you could say, okay, so when you give you give words or propositions or whatever, and when they are related, then you would say, okay, so when this is spreading, then the response should be faster, right? That would be enough. So you don't have to say, and now I collect data, because there are tons of data in this field already. But the patterns as such, you need to refer to somehow.
Thank you so much.
It's clear what I mean?
Yes, I got it. Thank
I
you.
mean, there's a lot of papers from your country. I mean, I know that you are very well educated in mathematics and these things, but often they are not related to any typical issues that the journal is concerned about. And in psychology, you need to have something with psychology, obviously, right? So otherwise you
Yes,
you
yes.
submit it to sociology or to political science or to computer science.
Yes, maybe I just you know, choose the wrong the wrong journal.
Yes, yes,
Thank
yes,
you so much.
yes,
Beg your pardon, Professor.
yes, please.
You hear me well?
Yes, yes, fine.
First of all, thank you for your precious lecture. My question is, can the class of drift models you mentioned during your presentation be applicable to the diagnosis or prognosis of some neuropsychiatric disorders which are accompanied with, let's say, some aberrance in decision-making or risk-taking processes, etc., etc.?
Okay, so in principle, of course, once you have, let's us, okay, so they all have some, these models always do something with selecting a response option, right? So when you have diagnoses or options, and then you say, okay, I have 5 different options. In principle, I mean, this was just for binary here, of course. So then you, in principle, you could, but so your idea is to put anything on. What would you put on the drift rate with a diagnosis then?
I don't know, maybe coming up with a task which poses 2 alternative choices,
Mm-hmm.
and present the patient with a scenario of decision making
Mm-hmm.
between 2 opposing equally beneficial choices. I don't know. I was just wondering over that.
You mean you want to compare groups with respect to different tasks, and then you want to interpret the parameters, so you have some. Yeah, of course, that's
parameters.
Yeah, you can do that. No, that's actually done. So that is done with all kinds of different groups, old and young, and what you have, and also for sure with some health problems. So I mean, the gambling term, the Iowa gambling task, for example, that can be mapped on easily on this. So as soon as you have some choices, then it's fine to use these models, and then you can say, okay, people with this or patients with this, they react, and that is reflected in a lower drift rate, for example. Yeah, of course you can. Yeah.
So these are easily applicable in clinical settings, you mean?
Yeah, I mean, that's these are in applications. Wow. So you mean like a diagnostic tool, really?
But okay, not a diagnostic.
Yeah, sure. I'm not so sure whether
But
this.
auxiliary tools.
Yeah. I mean, you can always, when you have data, then you can model the data, and then you say in this group of patients, it is they do, and then you, after you did all the modeling, and then you say this is reflected in, for example, yeah, as I said, in the drift rate or the parts, whatever you put on the drift rates, and that reflects the state of this patient group, or this patient even, right? So this is
so you mean what we need is more research into the field of neuroeconomics and its bridge to the translation of psychiatry. Some kind of okay. Lovely, thank you.
You're welcome.
Okay.
Okay.
Adele, many thanks again for coming.
Yeah.
And I hope you have a nice day.
Yeah, thank you. The same for you. Thank you so much.
Bye.
Bye.